So this is what we did in the morning, right? We talked about collisions of molecules with a wall of the vessel, and we found out that when that happens, we get the pressure given by this relation. Now we are going to simplify this relation further. Instead of having the relation in form of x, y and z separately, we'll try to combine all of that. Okay, so like I mentioned, average of Vx square, average of Vy square and average of Vz square is equal. So now if I'll write the kinetic energy of a single molecule, okay, translational kinetic energy of a single molecule, of one molecule, that is. So then that is going to be 1 by 2 mv square. But hopefully you remember that speed is nothing but the magnitude of the velocity. So this is what we get, right? So v is equal to under root vx square plus vy square plus vz square. Clear? Now if I'll square this, the square root would be gone, so I will get half mvx square plus vy square plus vz square, all of this being in a bracket, right? So this is the translational kinetic energy of a single molecule, right? Are these three steps clear? Now I want all of you to recall that animation which I had shown you. Again, the emphasis is understanding random motion. You see, what we have is, because the motion is random, there is no way that the value of Vx, Vy or Vz can remain constant. What I mean to say is, even for one molecule, the value of Vx, Vy and Vz will change with time randomly, because that's going to happen because of lots of pull. Look at a particular molecule, let's say molecule, and you're observing it, then its value of Vx, Vy and Vz rapidly, very quick. So such a case, writing a molecule like this is correct according to physics. Part of that was average kinetic energy. Average kinetic energy of all molecules. Again, kinetic energy translational. Don't forget that word. Please write translational over here. Okay, the average translational kinetic energy of all molecules. So to do that, I'm going to have to take average of K, which is going to be 1 by 2 m. Now mass of every molecule is same. Suppose you take oxygen gas, then mass of all oxygen molecules, that is O2 molecules, is going to be same. So mass is a constant, we don't have to worry about its average. What we have to do is we have to take average of Vx square, we have to take average of Vy square, and we have to take average of Vz. Okay, I repeat what I have said. When we take the average of translational kinetic energy of all the molecules, right, this is what we get. Now if we go over to the next step, 1 by 2 m. If you remember earlier, I told you that all the three are actually same, right? All these three are actually equal. That's what we did in the morning. That was the last thing we did here, right? I hope now you remember that. Okay, so that's why I can simply write this as, average of 3 times average of Vx. Okay, right? Because these three things, they are same, right? Okay, so this is what we have got. Now what we are going to do is we'll take this term, we will take this term from the previous step, the derivation, right? Over there had mvx square. Okay, where are we? Here, right? Over here, right? So when we took the average, we got it like this. Do you see this, everyone? That's what we are going to use. I repeat what I've said. That's what we are going to use. Okay, so average of vx square. The new things I'm writing in red. The average of vx square is nothing but pressure into volume divided by mass of gas. Okay, this is clear to you? So we take that and we go over there and we put it over there. So this will become equal to 3 by 2 small m pressure into volume divided by mass of gas. Okay, so that is the average kinetic energy, right? Okay, there is still scope to simplify this formula. Remember, there is still lot of scope to simplify, right? Okay, so this is what we have got. Now what do you think m upon capital M is? M upon capital M equal to 1 upon n, isn't it? Okay, so if I put that here, I'll get average kinetic energy of translation will be equal to 3 by 2 P into V upon capital N, right? Now I think you would be using this symbol in chemistry also. I'm not so sure though. I'm going to talk about something called number density. We're going to define, this is a new term if you don't know about this from chemistry. Number density means number of molecules. Number density means number of molecules per unit volume. Okay, if you want you can write it in that form. All right, okay, I hope that makes sense to you, right? Number density means number of molecules per unit volume. Yes, the mathematical form of this would be capital N divided by capital V. Again, number of molecules per the volume. So capital N upon capital V is written as small n. Okay, is written as small n, number density, right? If you think you might get confused, you can write it like this: nd, right? nd, number density, is equal to capital N upon capital V. So if you want you can put that here, right? Okay, so that's one thing to do. The other thing to do, આ બધું એક હું લાઈનમાં નથી કરાવતો, ડેરિવેશન જેવું નથી કરાવતો. Okay, there are so many different paths that you can go on, right? So listen to this carefully. There is another alternative. You can put nd of course here. There's one more alternative. Do you remember the ideal gas equation? PV equal to mu RT. Mu means number of moles. Okay, mu means number of moles. So if you do that here, in chemistry you might be writing PV equal to nRT. You can write n also, I don't have problem. अरे सिम्बॉल बदलाय तो कई फरक पड़े नहीं दिया. As long as the meaning is same, we are happy. Symbol तो હું તો અહીંયા x એ લખું, PV equal to xRT. You cannot stop me from doing that. Okay. So now if you put this P into V over there, so we get average translational kinetic energy equals, okay, let's go to this step, 3 by 2 PV. Instead of PV, we will write mu RT by capital N, right? We'll get 3 by 2 mu RT by capital N, right? So now, this is the time to understand what we have here. This is, listen to this carefully, this is the average translational kinetic energy of one molecule. It is the average translational kinetic energy of one molecule, right? Okay, again, don't lose track of what we are doing. We are talking about the average translational kinetic energy. Now, based on chemistry, I think you might be knowing this, that 1 mole is Avogadro number, that is 6.02 into 10 raised to 23. Okay, so mu moles, if it is N, okay, then the relation between these three things is as follows: mu equal to N upon Na. Are you aware of this relation to find number of moles? Okay, yeah, very good. You please remember it, it's very important. Okay, number of moles is N upon Na. So if I put that here, so I put value of mu, I've put the value of mu into R into T and then divided by capital N. So you see, capital N will get cancelled. Capital N means number of molecules, terms. Capital N for number of molecules. Sawari જ હતું. So no, Mahavir, you'll have to write things as we go on. So otherwise you can watch it on video later. So 3 by 2 N by Na into RT by N. So N cancelled, right? So now we have R upon Na. Have you studied that in chemistry? R upon Na. You know what is R, correct? So R upon Na is called Kb. Kb, that is Boltzmann constant. Actually, Stephen Boltzmann constant, right? Never mind. Boltzmann constant is good enough for. So this is Boltzmann constant, right? And its value we can find easily by putting value of R and Na. I hope I don't have to tell you what is R. R is the gas constant, yes. Okay, universal gas constant. So value of R in SI unit is 8.314 joule per Kelvin per mole. Okay, and yes, so if you are going to put that value of R in this equation, so this is also an important equation for us. So if you put that value, you get Kb's value, right? Kb equal to R upon Na is going to be 1.38 into 10 raised to minus 23, okay, joule per Kelvin. Okay, so that's the value of Kb. It's an important constant for physics. So let's continue with this. Therefore, average translational kinetic energy becomes 3 by 2, R by Na becomes Kb and T, right? So we started off with a lot of complicated expressions, but finally we have got something very, very simple, right? Okay, so this is an important formula. હવે આમાં આ ચેપ્ટરમાં એવું છે કે બહુ બધી ફોર્મ્યુલા તમે કહો એટલી હું તમને આપી શકું લખવા. ઓકે, બટ ઇફ યુ લર્ન ટુ ડિરાઈવ it's extremely simple. Okay, everything very simple, right? ખાલી આમ વેલ્યુ મૂકો અને ફટ કેન્સલ થઈ જાય બધું, તો ફોર્મ્યુલા નવી બની જાય. So it's as simple as that often, right? So average translational kinetic energy is 3/2 kBT, right? So far let's see what we have learned. ઓકે, હવે અત્યાર સુધીનું જેટલું છે જેટલું કરાવ્યું એમાંથી ઇમ્પોર્ટન્ટ રિલેશન્સનું એક લિસ્ટ બનાવ્યા છે, સો દેટ યુ ડોન્ટ ગેટ લોસ્ટ. આ ડેરિવેશન ઘણું મોટું છે, બટ દેર આર સો મેની થિંગ્સ ઇન્વોલ્વડ, રાઈટ? દેર આર સો મેની થિંગ્સ ઇન્વોલ્વડ ઇન ઇટ, રાઈટ? સો લેટ્સ મેક અ સમરી ઓફ વોટ એવર વી હેવ સ્ટડીડ સો ફાર. Most important part of chapter is over, let me tell you that, at least for kinetic theory of gases. Okay, here we go. So this is a list of important things that I would expect you to know now. Number 1, pressure proportional to temperature for a gas. Remember all this for ideal gas if volume is constant. Basically the three laws. Okay, basically the three laws. Then volume proportional to temperature if pressure is constant. Number 3, pressure is inversely proportional to volume if temperature is constant. Okay. Number 4, the ideal gas equation, that is PV equal to nRT or mu RT. You write whatever you want, I don't mind, right? So this is called the ideal gas equation. So these 4, right, these 4 are like properties or basics of what an ideal gas behaves like. Okay. Now, based on this, we have the next thing. Number 5, mu, that is number of moles. Word number of moles. Mu is equal to n upon Na, right? Is equal to n upon Na, and there is one more way to write mu equal to capital M upon small m. Oh, sorry, excuse me, not that, M0. Capital M upon capital M0, right? You might be aware of these things, right? But yet I'm going to note down or clarify the terms so that you don't have problem even at a later stage. Okay, so what are these terms? N, number of molecules. Na, Avogadro number, which I'm sure you remember. Okay, Na is the Avogadro's number. Capital M, if you look at the derivation, we use capital M. Capital M is nothing but the mass of the gas. Okay, and M0 or MO stands for the molar mass, excuse me, not molecular, molar. The two words are different, please don't get confused. Molar and molecular mass, they same no hoy, they are different quantities, and units એ અલગ છે, બધું અલગ છે. So please be careful, બહુ લોકો mistake કરતા હોય છે molar mass and molecular mass માં. So it's molar mass, not molecular mass of gas. ઓકે, આ રિલેશન આવડે છે કે ડિરાઈવ કરું? mu equal to m upon m0 આવડતું હતું? Okay, let's derive it. So I'll go to a new page and we'll come back to this, right? The list will continue. Okay, see, it is as follows: 1 mole of any substance, its mass, whatever mass it has, that mass is called molar mass, correct? I need definition, so molar mass symbol is M0. mm lucky, generally we use one lettered symbol, okay, that's why m0. Okay, so if there are mu moles, then how much will be the mass? That is m. Okay, then the mass is m. So we cross multiply karo to avi jase, right? So we have m into 1 equal to m0 into mu, right? Therefore mu equal to m upon m0. Understood? Right? By doing a simple cross multiplication, we get it. Ema kai biju complicated chhe nahi. Right? So this is the derivation of that relation mu equal to m upon m0. Tame n lagta hoy to n lagjo. I don't have any problem. Okay, shall we proceed with the list now? This derivation clear? Right. Okay. So here we are again. Right. So number of moles done. So there are two formulas for number of moles. Remember that there are two formulas for number of moles. Both are very useful. Let's go to the next thing. The next thing that we have derived or we have understood so far is that due to random motion of molecules, there are perfectly elastic collisions. There are perfectly elastic collisions. Okay, between what? Between two molecules, and also walls of vessel and molecules, right? So there are collisions between molecules and there are also collisions between walls of vessels and molecules, but all these collisions are perfectly elastic collisions, right? All these collisions are perfectly elastic collisions. Number 7, there is no preferred direction. Again, this is completely due to random behavior. There is no preferred direction, right? Number 8 is that velocity of molecules or velocity of a molecule keeps changing randomly, due to collisions. So what does that mean? We cannot say that a particular molecule is moving with a fixed velocity. It will move with some velocity for a short time, and then suddenly some collision will occur and velocity will change, and then we don't know what it will be. So like that, the velocities of every molecule, they keep changing, right, due to collisions. This number 8 clear? So you can say that there is some unpredictable behavior, right? And that is what is random. Random no meaning is unpredictable. So તમે predict કરી શકો તો એને random જ ન કહેવાય. Number 9. Now we come to the formula. Okay, so because every molecule, its velocity is changing and all that, there is no point talking about an exact velocity. કારણ કે તમે એમ કહેશો કે ઓકે this molecule has velocity 100 meter per second, એટલું બોલો એટલી વારમાં તો 5 વાર બદલાઈ જાય. Understood what I said? The velocities are changing so rapidly, that's why only average makes sense. Everything else is not that useful. So when we take average, the average squared of all the three components of velocities for the whole gas is equal, right? This is due to number 7. You can say that this is due to point number 7. Okay, this is due to the point number 7. And now because of that, when you find the average translational kinetic energy, this time I am writing T. T is for translational. Okay, this time I am writing T. Derivation માં નહોતું લખ્યું કારણ કે words માં લખ્યું હતું. હવે important point માં લખો ને ત્યારે symbol વ્યવસ્થિત લખાય તો યાદ રહે. So average translational kinetic energy, right, is equal to 3/2 m into Vx square for one molecule. Okay, આ બધું હજી for one molecule જ લખાવું છું, which you can also write as 3/2 kBt. Okay, so average translational kinetic energy, આ t અહીંયા લખો છે x, just one. This is average of translational kinetic energy 3/2 kBt. Okay, what are the terms here? Kb called Boltzmann constant. Okay, T for absolute temperature, capital લખ્યું છે, be careful. યાદ છે ને મેં તમને કીધું હતું, whenever we write capital, it's going to be the temperature in an absolute scale. That is, here we are going to use the Kelvin scale, of course, in SI units. Right? Also, please write meaning of KT. KT means what? Translational kinetic energy. યાદ તો છે ને, ટ્રાન્સલેશનલ કાઇનેટિક એનર્જી હોય, રોટેશનલ કાઇનેટિક એનર્જી હોય. ઓકે, constant say you can remember its value. Please remember kb's value. Now you see all the in number 10 what we have written, as a was to note karjo, this is just for one molecule here, right? Okay, these two formula are for what? For one molecule. એ કેવી રીતે ખબર પડે, સમજ જાય છે? Small m stands for mass of one molecule. I hope you understood that. Now if you do the same thing, અત્યાર સુધી આટલું શીખવાયું. Okay, this is what we have done so far, right? Okay, હવે આ લિસ્ટ અહીંયા હજી આગળ તો ઘણું લખવાનું છે, important points નું list છે. So now we will continue after deriving a few more things. Okay, so let's go to the next thing. Translational kinetic energy of gas. So far we were talking about average translational kinetic energy of one molecule. So for one molecule it turns out to be 3/2 kb. Okay, or you can also write, side માં લખું છું એટલે તમને યાદ રહે કેવી રીતે આવ્યું હતું. We can also write 3/2 m and then average of Vx square. Now if this is for one molecule, again this is for what? One molecule. હવે મારે બધા મોલિક્યુલ્સનું સાથે લખવું હોય, that is total. Okay, so I can say for the entire gas, that is for all molecules together, then do you understand that KT now, see, it's not an average anymore. I'll tell you why it's not an average. Listen to this carefully. Suppose I say that there are 10 students in a room or in a classroom. Let's say student number 1 has 3 pens, student number 2 2, student number 1 student number 1 has 3 pens, student number 2 has 2 pens, student number 3 has 1, 4 has 0, 5 has 0, 6 has 4, 7 has 3, 8 has 2, like that. So if I just add all the pens, then what I am getting is not an average. You understand what I am saying? if we find the total number of pens with all the students together, not average, just adding them. Okay, so what we are doing is not an average here. That's why for entire gas, that is together for all molecules. Did you understand? It's not an average anymore. Is this clear or not clear? I'm not writing the average because it's not an average. Nothing ખબર ન પડી ને એવું લાગે છે. Who has understood? Can you please raise your hand? પહેલા એક્ઝામ્પલ કમ્પ્લીટ કરી લે તો જ તમને બરાબર સમજ પડશે. સપોઝ these are the number of pens with student 3 2 1 0 0 4 3 કેટલા થયા? ચલો ને 5 સ્ટુડન્ટ્સ રાખો, 10 નથી રાખવા, 5 સ્ટુડન્ટ, easy enough. So these are 5 students. Earlier what we have found was the average number of pens. Average કોને કહેવાય? per student કરો તો average થાય ને. So what was that? That was this. Are you okay? And that would turn out to be in this case 6 by 5. That is nothing but 1.2. Clear? Average number of pens per student for one student, 1.2. Now instead of this, if you are going to take the total of the number of pens that all these students have in the entire class, let's say 5 students are there in the class. Okay, so if I find the number of pens with all the students, not just one student on an average, with all the students, then what's that number? It will be 6. Clear? આમાં તો કંઈ નો સમજાયું છે જ નહીં ને, બરાબર ને? ખાલી એડિશન જ કર્યું 6. ઓકે, so this is what we are finding. હવે આને કંઈ એવરેજ ન કહેવાય. This is not average, this is just addition. This is not an average. So there is no need for me to write average. Okay, so that's why I'm just writing KT. I'm not writing average. So now how much will be this KT? The idea is simple. Number of molecules multiplied by the average translational kinetic energy of one molecule. Yes or no? Is this clear? See, you can see that here also. આ 1.2 આવ્યું હતું, ઇન્ટુ પાછું 5 કરો તો 6 આવી જાય ને. That's what we have done. If I multiply it with number of students, the same thing I'm doing here. So if I multiply it with the number of molecules, then we'll get KT, which is the total translational kinetic energy for all the molecules. That is for entire gas. આ હજી translational જ છે, rotational ને એવું બધું તો પછી આવશે. So this is still only translational kinetic energy for the entire gas. So શું થાય? N into. Now what is this? It is 3 by 2 kBT. ચલો હવે આગળ. Okay, so if you look at what we have done in the previous few steps, then instead of n, I can easily write mu into Na, isn't it? પાછળના important points માંથી ગોતો ચલો. That instead of n I can easily write mu into Na. મળી ગયું ને? Okay, so if I do that, we have one more simple relation to use. Na into Kb. What is Na into Kb? What is Na into Kb? R, Na into Kb is R. So this will become 3 by 2 mu, Na into Kb is R and T. Okay. So this is the formula for translational kinetic energy of the entire gas, right? Don't forget the title. This is for the entire gas. એક મોલિક્યુલની અલગ છે. જો એક મોલિક્યુલમાં છે ને અહીંયા Kb આવે, એવી રીતે અહીંયા R into mu આવે. Okay, you can also do it as follows. For 1 mole of gas, for 1 mole of gas, Kt equal to 3 by 2 RT. Okay, આ ત્રણેય ફોર્મ્યુલા એક જેવી જ છે. They may cause confusion if you try to rote learn it. હા, અરે આખો ચેપ્ટર કેમેસ્ટ્રીમાં છે નંદિની, આખો ચેપ્ટર, બરાબર ને? So if you try to rote learn it, you will have trouble. Okay, instead do it carefully, right? See, here's the clever idea. ગમે ત્યારે છે ને one molecule નું કંઈ આવે ને, then you are going to find that you will have Kb in it. I repeat, formulas that have it for one molecule, they are going to have Kb. સમજાણું? On the other hand, the ones for 1 mole will have R. જ્યાં Kb હતું ને અહીંયા R આવે. The relation between them is like this, and that's the only reason why we have it that way. Okay, you can remember it like this: R equal to kabhi na. Okay, that will help you remember. Okay, so yeah, so for 1 mole it is 3 by 2 RT, and suppose you are doing this for more number of moles, then it is 3 by 2 mu RT. Right? I hope this is clear. હું તો આ એક જ યાદ રાખું છું, આનાથી બધું જ થઈ જાય. Right? So for the entire gas, the translational kinetic energy of the gas is Kt equal to 3 by 2 mu RT. Okay, this is again a very important relation that we have got here. બધી છે દિયા, સેકન્ડ, થર્ડ, ફર્સ્ટ, એ ત્રણે ત્રણ એક જ છે ખરેખર. This is just like for 1 mole, for mu moles, એનાથી કંઈ ફરક નથી પડતો. આમાં mu equal to 1 મૂકો તો શું થાય? આ આવી જશે. Yes or no? So I would say don't burden yourselves up. એક આ યાદ રહી જાય તો બહુ થઈ ગયું, આનાથી બધી થઈ જાય એવું છે. રાઈટ? હા, અમુક સ્ટુડન્ટ્સને પછી થોડો પ્રોબ્લેમ થતો હોય છે કે આ કેવી રીતે આવે, એમાંથી એ આવી જાય. If you act smart, one molecule is actually 1 upon Na number of moles. જો તમારું કેમિસ્ટ્રીના મોલ્સનું ને એવું બધું એકદમ ક્લિયર હોય તો તમને આ સમજાઈ જશે. Right? One molecule is actually 1 upon Na number of moles. So એ એમાં મૂકી દો ને તો એ થઈ જાય. So I recommend that you remember this definitely. અને સપોઝ પછી આ ન આવડે તો આ યાદ રાખો, this line. Okay, the first one. ચલો હવે આટલું થઈ ગયું. Now inference. Inference એટલે હવે conclusion. આટલું derive તો કર્યું, but this is really ground breaking derivation. So what have we done? We have got a relation between kinetic energy, translational kinetic energy of molecules or of the whole gas, જેના molecules આપણને દેખાતા નથી. Don't forget, we cannot see the molecule, but we have related that translational kinetic energy with something that we can easily measure, that is temperature. So this formula gives you a relation between something that you can never see, never even think of measuring. કોઈ એમ કે ચલો મોલિક્યુલની કાઇનેટિક એનર્જી મેઝર કરો, it's nearly impossible to do that directly. Why so? First of all, they are very small. Second thing, their velocities are changing randomly. બરાબર? કોલિઝન કેટલા બધા થતા હોય, તમે હજી કંઈક એક્સપેરિમેન્ટ કરીને મેઝર કરવા જશો એટલી વારમાં તો 2 વાર ચેન્જ થઈ જશે. ઓકે, એક વાર નહીં, કેટલી વાર ચેન્જ થઈ જશે. So it's very tough to actually measure kinetic energy of molecules. But this equation gives you an amazing relation. It's that the kinetic energy of translational kinetic energy of all of that entire gas can be measured just by measuring temperature. Okay, just by measuring temperature and number of moles. એમાં કઈ મોટી વાત નથી. Number of moles તો easily measure થઈ જાય by using mass. Okay. Also, this formula once again gives temperature its definition. So here is the definition of temperature. The measure of random motion kinetic energy. चलो आम न लगाओ, थोड़ું व्यवस्थित લખાઓ. તમને કદાચ કેમેસ્ટ્રીમાં ન આવ્યું હોય તો the measure of kinetic energy of molecules due to their random motion. Due to their random motion is called temperature or absolute temperature. Okay, the measure of kinetic energy of molecules due to their random motion is called absolute temperature. આનો meaning શું થાય ખબર છે? That how much is the temperature? If you want to decide that, then you should look at the kinetic energy of the molecules due to their random motion. Okay. ના, ટ્રાન્સલેશનલ નહીં આવે, બરાબર? કારણ કે હજી તો એકદમ બેઝિક આપણે કવર કર્યું છે. ઓકે, you can actually have any kind of translational energy and this sentence would still be true, right? એટલે અહીંયા ટ્રાન્સલેશન લખવાની જરૂર નથી. ઓકે, સો ટ્રાન્સલેશન લખો તો ખોટું નથી અને ન લખો તો ખોટું નથી. That's what I said, right? It's fine even if you don't specify translational, it's okay. So I was saying that if you want to measure absolute temperature or if you want to relate that what is temperature really, okay, આ question એક problem હતો. For example, earlier people thought that temperature means how much heat it contains. યાદ છે, heat was thought to be like fluid, right? So people thought that if something has more heat, it means it is having higher temperature. And if something has less heat, it has lower temperature. But that's not true because heat is not a substance. Remember, heat is not a substance. It is not like a fluid. मैं તમને સમજાવ્યું હતું ક્લાસમાં, બરાબર ને? Heat is not like a fluid. So that definition of temperature is wrong. This definition of temperature is much better, right? It's a measure of the kinetic energy of the molecules due to their random motion. એટલે અહીંયા random motion બહુ important છે. Let me give you example. Suppose this is a vessel. Okay, let's say there's some gas in it. Okay, closed vessel. Now this vessel itself is stationary. You understand what I'm saying? Let's say this vessel itself is stationary. All right. But that does not mean that kinetic energy of translation is zero. This is nonsense. It is zero no ave, because the molecules inside would be going here and there. Do you understand what I'm saying? Yes or no? So you should compare two situations. Suppose this is a vessel whose inside temperature, to understand this thoroughly, let's compare two situations. Suppose this is a vessel with a gas inside and the temperature of the gas inside is, let's say 373 Kelvin, for example, right? And this vessel is stationary. The vessel is stationary, okay, at rest. Now if you consider another similar vessel with same amount of gas filled in it, right, and temperature again equal to 373 Kelvin. But this time again the molecules are definitely moving on the inside. Okay, but this time this vessel is not stationary. Let's say vessel is moving and at speed, for example 10 meters per second towards the right side. So આ બે કેસમાં temperature same જ આવે. Listen to this carefully. In both of these cases the temperature is same. But still, listen, but still, if you take this whole thing as system, then the kinetic energy in case 2 is greater than kinetic energy in case 1. કેમ ખબર છે? કારણ કે અહીંયા આ vessel move થાય. But still the kinetic energy of translation of the gas molecules, kinetic energy of translation of the gas is still equal whether in case 1 or in case 2. Did you understand this equation and this equation? તો આમાં કેમ એક્સ્ટ્રા એનર્જી છે? કારણ કે વેસલ મૂવ થાય. વેસલની પોતાની કાઇનેટિક એનર્જી. Vessel's kinetic energy is not random motion. Remember, do you think if you take a vessel, let's say you take a balloon filled with gas અને balloon ને આમ move કરાવો તો શું balloon random motion કરે? Not at all. Understood? So the important thing to understand is that kinetic energy does not indicate temperature. ઘણા લોકો છે ને શોર્ટકટ મારવામાં છે ને મિસ્ટેક કરી નાખે. ઘણા લોકો એવું વિચારે કે kinetic energy of molecules and temperature are related. તો આમાં તમારી બહુ મોટી ભૂલ થાય છે. The mistake is you forgot this. આનું શું? So temperature is related not with kinetic energy of molecules. It is related with the kinetic energy of molecules because of their random motion. એટલે એમાં જે motion non random હોય ને એ નહીં ગણવાના. For example, moving this vessel is not random motion. Understood? That's why you don't have to consider that. Okay, so make sure you see this difference. Right? We will definitely come back to this point in more detail later. એટલે એવું નથી કે આ તમને નહીં સમજાય તો ચાલશે. આગળ ક્યાંક નડશે તો ખરું. હા, પણ માઇન્યુટ ડિટેલ્સમાં જાઓ તો પછી તમે ઉપરથી ભણવું હોય તો કંઈ ફરક નહીં પડે. Right? So that is what temperature is. Right? So to the list of important points that we have studied so far, time to add a few more. 10 સુધી થયા હતા. Number 11. For a gas KT equal to 3/2 mu RT. No, in second vessel randomness will be same as first vessel. Okay, just that the whole vessel will move. That motion of vessel is not random. Okay, that's why temperature is same. So for a gas KT equal to 3/2 mu RT, right? Again this mu stands for mole. એટલે for 1 mole લખવું હોય તો એ બધું અહીંયા લખું છું. You are free to omit if you think you have understood this completely. Okay, so that's about translational kinetic energy. Right? Now let me just check if there's a question in the book. અચ્છા, આ જે લાસ્ટ 3 છે ને એના માટે બુકમાં એક નામ આપ્યું છે. When I was flipping the pages I saw the title and it's a good title. These 3 relations which somehow connect the translational kinetic energy with temperature. Okay, એના માટે બુકમાં એક નામ લખ્યું છે. It is called kinetic interpretation, kinetic interpretation of temperature. એનો મતલબ what is the relation of motion with temperature? Okay, he indicate કરે છે that kinetic energy of random motion is linked with temperature. એનો meaning એવો થાય. So let's go and see if we can solve the question here. Yes. Example 13.5. Example 13.5. Okay. Everyone got to that? It's in chapter 13, page number 330 in my book, may be different. Example 13.5. Okay. So the question is, a flask contains argon and chlorine. So inside a flask, this is a flask, whatever shape, no problem, contains argon and chlorine, both the gases, in ratio 2:1 by mass. And 1 go and 2. Then m1 upon m2 is 2:1. So 1 is argon for us and 2 is chlorine. Okay. The temperature of the mixture, so they are all mixed here, right? The two gases are mixed. Temperature of the whole thing is 27 degrees Celsius. Obtain, number 1, there are two parts, right? Let's solve first part at least. So number 1, obtain the ratio of average kinetic energy per molecule. Okay, so this question is wrong. Everyone, make a change. એમાં છે ને એડ કરવો પડશે એક વર્ડ, એવરેજ ટ્રાન્સલેશનલ કાઇનેટિક એનર્જી, એવું કરી નાખો. એવરેજ ટ્રાન્સલેશનલ કાઇનેટિક એનર્જી એવું કરી નાખો. Did you make change in the question? Okay, basically solution doesn't match. મને યાદ છે લાસ્ટ યર એ ક્વેશ્ચન કર્યા પછી એવું થયું હતું કે લે આનો આન્સર તો અલગ આપ્યો. નેવર માઇન્ડ. પર મોલિક્યુલ, જો ક્વેશ્ચનમાં શું પૂછ્યું છે, એવરેજ ટ્રાન્સલેશનલ કાઇનેટિક એનર્જી પર મોલિક્યુલ. ઓકે, એક મોલિક્યુલની એવરેજ for both of these. So our number 1 એટલે for argon અને our number 2 for chlorine. So let's divide. Formula શું છે? For average translational kinetic energy 3/2 kBT. Do you realize both will be at same temperature whenever you have a mixture of gas, and the temperature of system is 27, so both have same temperature, yes or no? So આ બધું કટ જ થઈ જશે ને. So what do we get? 1 means the answer will be 1:1. The kinetic energies are equal, so answer is 1:1. Understood? કંઈ કરવાનું નહોતું, ફાલતુ ક્વેશ્ચન હતો. સપોઝ અહીંયા 27 ને બદલે કંઈ પણ આપ્યું હોય, 600 કેલ્વિન આપ્યું હોય તો still no problem, this would not change. Okay, yeah, the key thing is translational. Translational no હોય ને તો અલગ આન્સર આવે. Okay, but we'll see that later. So part 2 of this question and more theory, more derivation tomorrow. All right, sorry, on Monday that is. Okay, goodbye everyone. Please revise the important point. યાદ રહી જવું જોઈએ, બરાબર ને? Goodbye.